Last time we saw how the perceptron algorithm, those 4 lines of code, could be adapted to learn quadratic decision boundaries. The trick was to expand the input features, a trick known as basis expansion. Now it turns out that these expanded inputs can often be inconveniently large enough to be impractical. And we'll see how we can get around this problem by using the kernel trick. So the focus today will be developing the kernel trick for quadratic decision boundaries and culminating in the kernel perceptron algorithm. Okay, so first a quick recap. So last time we were looking at the situation where we want to learn a quadratic decision boundary, and we were wondering whether we could use our standard linear classifier technology for doing this. And we saw that we really can do this by expanding the input features. So we take the original features x, and we create an expanded feature vector, phi of x, that includes the original features, their squares, and also pairwise products like x1 and x2. Now the reason for doing this is that any boundary or any function that is quadratic in x is also linear in phi of x. And therefore, we can learn a quadratic boundary in the low-dimensional space by just learning a linear boundary in the higher dimensional space of phi of x. So here is the perceptron algorithm with basis expansion. It's exactly like the usual perceptron algorithm, except that every time we have an x, we replace it with the higher dimensional representation phi of x. And last time we saw some pictures of the kind of quadratic boundaries that this produces. So this is all well and good, but there is one fairly significant problem. And that is that these expanded feature vectors can be very high dimensional. So let's look at the situation of MNIST, for example, the MNIST dataset of handwritten digits. There, the original dimension, the dimension of the data points x, is 784. What is the dimension of phi of x? Well, we actually saw a formula for this last time, but roughly the dimension is about d squared. And in this case, it works out to 308,504 dimensions. This is the space it takes to write down a single data point. Okay? Now this is way more time and way more memory than we want to spend on individual data points, and it's enough to render this method impractical. So, is there anything we can do? And it turns out that there is. It's called the kernel trick. The idea is that we can take the same algorithm and implement it without ever writing down anything in the higher dimensional space. How do we do this? Okay, let's take this one step at a time. So here's the algorithm that we want to implement, the perceptron algorithm with basis expansion. Now, a bunch of the vectors that we're dealing with over here are potentially very high dimensional. So in the case of MNIST, the x's are 784 dimensions. The phi of x's, we said, are over 300,000 dimensions. What about W? Is W 784 dimensions or 300,000? Unfortunately, it's 300,000. Well, W is the final answer. We can't avoid writing that down, surely. Well, actually we can if we move to the dual form of W. Okay, so last week we talked a little bit about the dual form of the perceptron algorithm. And the main observation over there is that the W vector at any given time is of this form. You see, we start W at 0, and the only way we modify it is when we are updating on a specific point. And when we update on the ith point, what we do is we add yi, phi of xi, to w. So at any given time, w looks like this, where alpha j is exactly the number of times we have updated on the jth point. So instead of working with w, we can instead equivalently work with the coefficients alpha 1 through alpha n. There is one of these coefficients for each data point, and we can put them together into a vector alpha. Okay? And from alpha, we can, if we like, recover w. Okay, so we have solved the problem of w. We're just not going to use it at all. Instead, we're going to use the dual representation alpha. Okay, so the first problem is solved. But now, it does look like in order to classify a point, we need to compute w dot phi of x. How do we do this without actually writing out w? Well, again, we use the dual form of w. Okay, so w dot phi of x, well, what is w? Let's just plug in this formula right here. We have the sum over j of alpha j, yj, phi of xj. And we want to take this whole thing dot product with phi of x. Now we can bring phi of x inside the parentheses, and then we get exactly this formula over here. So we don't need w after all. We can work directly with the coefficients alpha 1 through alpha n. Okay, so to compute the dot product w dot phi of x, we simply sum over all the data points of the coefficient for the jth point, alpha j, the label for the jth point, y of j, and the dot product of phi of xj with phi of x. Okay, so we have eliminated w effectively. Okay. But there's still something that's a little bit troubling. It looks like we have to compute these dot products over here. The dot product between two, say, 300,000 dimensional vectors. How do we compute these dot products? Don't we at least have to write the vectors down? Surprisingly, it turns out that we don't have to. It turns out that for any x and z, we can compute the dot product phi of x dot phi of z without writing down either phi of x or phi of z. And let's see why this is the case. Okay, so let's start with the two-dimensional case. So we have data points x with two features. And in this case, the expanded representation phi of x contains those features, as well as their squares, as well as the pairwise term x1, x2. Okay. Now let's actually tweak this a little bit. Okay, we'll throw in an extra feature that's identically 1, and we'll stick a square root 2 in front of some of the features. This is linear in the original phi of x, so it doesn't really change things. Any function that's linear in the original phi of x is linear in the new phi of x, and vice versa. Okay, so we'll work with this slightly modified representation. What is the dot product phi of x with phi of z? Let's write it out. Okay, so phi of x contains 1 square root 2 times x1, square root 2 times x2, x1 squared, x2 squared, and square root 2 x1, x2. And we're going to take the dot product of this with phi of z, which is 1 square root 2 z1, square root 2 z2, z1 squared, z2 squared, and square root 2 z1 z2. Okay, so let's multiply this out. We get 1 plus 2 x1 z1 plus 2 x2 z2 plus x1 squared z1 squared plus x2 squared z2 squared plus 2 x1 x2 z1 z2. Okay. Now it turns out that you can simplify this expression. it's actually equal to 1 plus x1 z1 plus x2 z2 squared. Okay, and if you stare at it a little bit, you'll see that this is true. Okay, so in other words, it's equal to 1 plus x dot z squared. So the dot product between the higher dimensional vectors is the dot product between the original low dimensional vectors plus 1 squared. Now exactly the same thing holds when the original vectors are d-dimensional. Okay, so we start with x that is d-dimensional. We look at the expanded representation, and again we tweak it a little bit. We add in a feature that's identically 1, and we put some square root 2's in there. And if you compute phi of x dot phi of z, it turns out that it's exactly x dot z plus 1 squared. So in the case of MNIST, to compute the dot product between two high-dimensional vectors, two 300,000 dimensional vectors, you simply compute dot products between the original 784 dimensional vectors, and then you take the answer, you add 1, and you square it. It's very simple, and it's something we can do efficiently without ever writing down anything in the 300,000 dimensional space. So here is the kernel perceptron algorithm in two different forms, a primal form and a dual form. Okay, so the setup is we have a data set, x1, y1 through xn, yn. Okay. In the primal form, which is the form that we use with basis expansion, we're working with w and these expanded representations phi. This is a perfectly correct algorithm, but the downside is that w and these phis can be extremely large, so large as to be impractical in many situations. To deal with those cases, we can instead use the kernel trick and work with the dual form of the algorithm, which is shown down here. Here, we avoid w altogether and work alternatively with the vector alpha, the vector of coefficients. The updates in this version of the algorithm are extremely simple. We start by setting alpha to 0 and the offset b to 0, and then we cycle through the data. Each time we come to a data point that's misclassified, let's say it's the ith data point, all we do is to increment alpha sub I and add the label y sub I, which is either +1 or -1, to b. These are childishly simple updates. The only thing that looks remotely complicated is that we have to compute these dot products between the high-dimensional embeddings of the data points. And as we've seen, this is something we can do efficiently without ever writing down the high-dimensional vectors. Now, to classify the data point, to classify a new test point, we again use the dual form of w, and we use this rule. Okay, so this is equivalent to doing the sine of w dot phi of x plus b. Okay, a linear classifier in the high-dimensional space of phi of x. Now, last time we saw some of the boundaries that the perceptron algorithm with basis expansion yielded. Okay, so here's a situation that's not linearly separable. And the perceptron algorithm gave us this boundary, which looks like part of a parabola. Okay? Now, the points that are shown in bold, like this point over here, are points for which alpha is not 0. Okay, so the alpha vector has got a coordinate for every single data point, and in this case there are 36 data points, so alpha is 36 dimensional. Some of those features are 0, okay, and the ones shown in bold over here are the coordinates corresponding to points on which there were updates, okay, and those are the non-zero alpha sub i's. Here's another example, again not linearly separable, and here's a boundary that the kernel perceptron algorithm yielded. In this case, almost all of alpha is non-zero. there are just a few points in the corners on which no updates were ever made. Now, these are two-dimensional data sets, and in this case, the expanded feature vector is only 5-dimensional. In situations like this, we could easily use either the primal or the dual form of the algorithm. Okay, they would both be perfectly efficient. But when the dimension of the data gets higher, when it gets to 100, say, or above, the primal form of the algorithm can become highly inefficient just because the expanded vector phi of x becomes so large. In those cases, the kernel trick is what saves us and allows us to use the dual form of the perceptron algorithm. Okay, that's plenty for now. We've seen how the perceptron algorithm, just a few lines of code, can be modified to efficiently learn quadratic decision boundaries. Next time, we'll take this much further and show how we can deal with boundaries that are arbitrary polynomials. See you then.